Okay, I hope this video finds everybody well. We're going to more formally establish the logic of hypothesis testing, which we like briefly introduced with the informal discussion of the popcorn kernels. So, just a quick review of the popcorn kernels. So, our whole goal, beginning with the popcorn kernels, is just to understand the logic and then always answer the questions: what do I expect to happen, and what actually happened? Okay. We'll learn how to establish a set of hypotheses and criteria to make a conclusion about a parameter. And some of the vocabulary here is very important, so I'm going to try to emphasize a few things. Parameter always refers to a characteristic or a value associated with the population. So let's just quickly review the popcorn from yesterday. So yesterday, or the previous video, whenever you watched it, was about proportion of popcorn kernels that would not pop. So I had a bag of popcorn. My guess was that 15% of those kernels would not pop. And we went and kind of like argued, was my guess good or was it not? And that's really what hypothesis testing comes down to. Like, is the claim true or is it not true? And so more formally, this is what we talked about. Like, I introduced this idea of how you argue and decide. But to do that, you need to know what a parameter is and what the population is. So our parameter of interest to us was the true proportion of unpopped kernels in this population of all kernels from this given company. So I had a specific company, the popcorn I was using, and really I was interested in what proportion of all of those kernels would remain unpopped. Okay, and we denote that by P. That's P without the hat. P stands for the population proportion of unpopped kernels for this company. So what do we do? Like, we were trying to figure this out. Well, obviously you can't get all of the popcorn kernels from this company and pop them all. So we took a sample, and our sample was this bag, and we could argue that it's a kind of a random sample because when the kernels come off the line and they get filled in the bags, they're pretty much randomly sorted. So we had a random sample of, I believe it was like 262 kernels, and so we were trying to figure out, is my 15% guess okay, or is it not okay? Like, is it reasonable or not? Okay. So our hypotheses, we had a couple different hypotheses. The initial hypothesis, which was my guess, was that P, the true proportion of unpopped kernels, would be 0.15 or 15%. The alternative hypothesis, which is an alternative explanation, was that, if I was wrong, I personally felt that if I'm wrong with my 15% guess, then I think the proportion is probably actually higher than 15%. So I had a initial guess and then an alternative explanation if I happen to be wrong. So then here's the really important part. Like, what rejection criteria did I use to reject my initial guess, which was my guess expectation, like what I expected to happen, in favor of my alternative. So what I said was, it was just a very informal argument. It's like, okay, if I pop this bag of popcorn I have here and I find that the sample proportion, so the proportion that I get from that bag of unpopped kernels is larger than 0.2 or 20%, I decided that, my initial guess of 15% is probably not right. Like, 20% is probably too far away from my initial expectation for me to believe that I guessed correctly. So I expect 15%. If I get 20% or more, then I'm going to start to question whether or not I guessed correctly. And I would probably reject my 15% guess. So we would say we would reject my hypothesis. So here it is. What did my sample data actually tell me, and what conclusion did I make, and why? So I took a random sample of those 262 kernels, and I found 77 unpopped kernels of those 262. So that told me P hat, the sample proportion, was 0.29. So our sample, we observed 29% of the kernels remained unpopped. My rule for rejecting my guess was 15%. My rule was, if my sample proportion was larger than 0.20, which it was 0.29, I would reject my initial guess in favor of the true proportion actually being larger than 15%. And that's what happened. The reason I rejected my 15% guess is like 0.29. I mean, it's almost 30%. It's really far away from what my initial expectation was. When I opened that bag, when I popped those kernels, when I popped the kernels, I expected 15% of those kernels to remain unpopped. I actually got 29%. So it's pretty high compared to what my guess was. So since the 29% is, pretty far away from what I guessed, I'm going to go ahead and say that my initial guess is probably not correct. The 29% is pretty unlikely to occur. Okay. So, how did my conclusion depend on my initial guess? Well, it completely depends on my initial guess. If my guess was closer to what I actually got in my sample, the better I would feel about my guess. So, for example, if I would have guessed initially that let's say I would have guessed 27% of the kernels would remain unpopped, and then we actually popped the bag and I got 29%, I'm going to feel pretty good about 27. I'm going to be like, whoa, I'm a pretty good guesser. So, your conclusion is dependent upon what your initial guess was. I mean, it has to be. I think everybody listening to this would agree that if you would have guessed that 0% or have a proportion of 0 unpopped kernels, I think you all would have felt like, well, that's not going to be right, because it's pretty unlikely that I'm going to have 0 unpopped kernels. So, that would be a very extreme situation, but your initial guess certainly influences your conclusion. Okay. So that's the logic. I mean, you really, all I did was I established a rejection rule. I compared what I expected to happen, which was my hypothesis, to what actually happened, which was my sample data. And the further away the actual data gets from what you expect, the less likely it is that what you expect is actually true. And that's really it. So that's all we're going to do is compare. So let's look at another example. And this new example here, I'm going to go ahead and introduce some vocab too. Okay. So the other one we could do is like test M&Ms. So this is a claimed color distribution of all M&Ms put out by the company. You can see is July 2006. So Tony doesn't think these claims are correct. In particular, he thinks the actual proportion of blue M&Ms is less than advertised. So to test the validity of this claim, Tony got a bag of M&Ms, standard M&Ms. You're not doing like the peanut stuff, just regular M&Ms, and finds that 7 of the 44 M&Ms are blue. So he is testing this claim right here, 24%. So let's go set this up a little bit and kind of figure out how we evaluate this. So what is the parameter of interest to Tony, and what is the population of interest? The parameter of interest to Tony is P, the true proportion of blue M&Ms produced in the population of all M&Ms. So like he is testing this claim made by the company that 24% of all of their M&Ms produced are blue. So that's the parameter of interest. The population of interest is population of all M&Ms. Okay, what hypotheses is Tony testing? So what did Tony expect when he opened the bag? So the initial hypothesis is the true proportion is 0.24. Because according to the company, when Tony opens his bag of M&Ms, he should expect to get 24% blue. So the initial hypothesis is 0.24. The alternative explanation is what Tony's skeptical about. He thinks that the true proportion might actually be less than 24%. So he has two hypotheses: the initial hypothesis, which is the claim, what should happen, what he expects to happen, and the alternative is an explanation of what happens if that claim is wrong. So according to the company, Tony should expect to get 24% of the M&Ms to be blue when he opens that bag. So a little vocab here in purple. Okay. We call an initial hypothesis in statistics, we call this the null hypothesis. Null stands for initial. Those of you who've seen subscript with zeros before, that always means the beginning. We denote it with capital H with a subscript of 0, and that is always our initial guess and what we expect to happen. So this is our expectation. The alternative hypothesis, denoted with capital H and subscript A, is the alternative explanation if your guess is if your initial guess is wrong. So for this scenario, here's how we write our hypotheses. We write the null hypothesis is P is 0.24. That's what we expect to happen. We expect 24% blues. The alternative is that if it's wrong, then we think the proportion is probably going to be less than 24% blues, or less than 0.24. Okay, so this is the way we write hypotheses in statistics. The null hypothesis is your expectation. Alternative is the explanation is if you are wrong. So what rejection criteria excuse me, will we use to determine if the claim is wrong? So before, in the other example, I established it. I said, if I get a certain proportion of unpopped kernels, I'm going to reject my 15% guess. So we established the rejection criteria using probability. That is a formal way of doing that. But you are the one who sets that probability. So we call that a significance level. Represented by the Greek letter alpha. This will tell us when to reject our null or initial hypothesis. Put that in there, the null hypothesis, and when to not reject it. Okay, just like our other rule. We are going to use a 5% significance level for our test. So here's what this means. That means if our sample data, or worse, or more extreme, occurs less than 5% of the time under our initial guess, which our expectation is 24%, then we reject the 24% claim. So what this is saying is, if our sample data occurs with a very low probability, if the company actually produces 24% blue M&Ms, then we will have to reject that 24% claim. Okay, and you'll see what I mean by that in a minute. But we call this the significance level. Common significance levels are 5%, 10%, and 1%, and they establish the rejection criteria for your test. So really all this comes down to is we're going to find a probability and compare it. Is the probability less than our 5%, greater than our 5%, and make a decision. So what we need to do is we need to establish, so we're going to simulate opening bags of M&Ms if the company's claim is actually true. So we can build the distribution of sample proportions. There's a lot of words going on there, but you're going to build a distribution, a plot of, we're going to use a dot plot, of sample proportions. So we're going to open up many, many, many bags of M&Ms and calculate the proportion of blues. And we're going to build this distribution that we would expect to occur if the M&Ms actually produce 24% blue. Okay, so here's what this looks like. So I have this set up to we have a hypothesis of 24%. So and what we're going to do is we're going to take a sample from this population where the M&Ms, like from this factory, M&M factory produces 24% blues. So we're going to take a sample from this factory or open a bag. Okay, we're going to open a bag of 44 M&Ms because that is what Tony had in his bag. So let's just take a sample. Let's just take one sample right now, one random sample from this population. So I add a sample. Okay, so here's what this means. It means I took one sample from the population of M&Ms that has 24% blues. And what I actually got was this right here, this sample proportion. In my sample, the first one with 44 M&Ms, I got 20.5% or 0.205 were blue. And like we expect 24%. So 20% It's not that bad. It's pretty close to what we expect. Let's do it again. So now you go and you buy another bag. You go buy another bag of M&Ms. Open it up. It's got 44 in there. You take a sample. Okay, this time, the most recent. Okay, this time they had 29.5% blues. So this one right here had a little bit more, a higher proportion or percentage of blues than the first bag. So you do it again. Take a third bag. Okay, this one had 22.7. Okay, pretty close to 24. That's your third bag. Let's do it a fourth time. The fourth time, oh, a little lower one. This one only had 13.6% blue M&Ms in their bag of 44. So as what we're doing is we're taking a giant container of M&Ms filled with 24% blue, and we're just pulling out randomly 44 of those. And every time we do that, we calculate a sample proportion, which is denoted by p hat, and we figure out the proportion of blue in that sample. And if we do this, we've done this 4 times now. Let's say we do this another 296 times. It'll give us a nice even 300 random samples here. Take a look at what happens. When we do this 300 times, look at what happens. This distribution, we've talked about CUS. It's a good review time here. What's the center of this distribution? Well, it's clustered around 24, isn't it? Like it's pretty close. It says right here. In fact, the average is 23.8%, which makes sense because that's what you expect to occur. So this whole distribution here is centered around 24%. We see that common proportions probably are from about 16, 17, 18% to about 31, 32% blues. So, I mean, every time you take a sample, you're not always going to get 24%. There's some variation to it. Otherwise, why would we even have statistics? There's some variation in that number. So, but you do see that it clusters around 24%, which is good because that is what we expect to happen. So we have built a distribution, should look pretty interesting to you. We have built a distribution that is what we expect to occur if the M&M company actually produces 24%. Okay, so I'm going to leave that up here for a second, flip back to my other screen. So we built that distribution. So it says, how is this distribution consistent with the company's claim? So I put on there 300 sample proportions. Like I mentioned, they tend to cluster around the 24% as they should because that is what we expect to happen. Okay, so we have this distribution of what we expect to happen when we open 300 bags of M&Ms. Okay, we have a distribution of the proportions of blue M&Ms in the samples, and we did 300 samples. Okay, so we have a pretty good idea now of what we should expect to occur. Then the most important part is you look at what actually happened. Look at the real thing. Simulation, we learned, was, you kind of fake it till you make it, because you can, and you can use some assumptions, like we're assuming the 24% claim, to develop what we should expect to occur. So what actually happened when Tony opened the real bag of M&Ms? And where does this sample data fall in this distribution? Tony's real bag of M&Ms had 7 of 44 M&Ms that were blue. That's what he found. If you calculate the sample proportion, that was 0.16. So Tony found 16% of blue M&Ms in his sample. Where does that actually fall? Let's take a look. So if you look at the expected distribution, 16% is like right here. So we can see that, a bunch of times that happened when we were doing our simulation. But Tony's bag would be one of these. So his bag of M&Ms falls here. Okay, so we know exactly where he falls in our distribution, on the left side of the curve, on the left tail. But he falls in one of these. The bag falls there. Okay. So we see where that is, and we know where Tony's bag actually fell. So now we need to go and make our conclusion. So compare what Tony expected to happen, initial guess, which was 24%, to what actually happened, the sample data. The sample data is your evidence, okay, for what is actually going on. So, what conclusion should Tony make and why? Tony expected to get 24% blue in a sample, but only got 16% blue. So Tony needs to look at the rejection criteria that we established. And our criteria was if our sample data or more extreme occurs less than 5% of the time, we will reject the claim made by the company. So really, all we need to do is figure out the probability of our sample data occurring or more extreme, even worse. So in this case, something like less than 16% blue, so maybe 10, 12. So we're going to look at that and find the probability of that occurring. So the way we can do that is just look at your dot plot. If you look at your dot plot, let's count the number of dots that are less than or equal to what we got, 16%. This region right here. This region contains all of the sample proportions that are at 16% or worse, like really, really low. Okay, and we see that there are 14.3% in this region. In other words, according to the simulation, there's about a 14.3% chance that we see our result, which is 16%, or lower or worse. Okay. Well, let's look at that. Well, our rule was, if this probability is less than 5%? Well, clearly it's not. So 14% is not smaller than 5%. So 14.3, we got 14.3% of the time we would get 16% at blue M&Ms or less in our sample if the 24% claim is true. Since 14.3% is greater than the 5% criteria, the significance level, we do not reject the 24% claim. It is possible that M&Ms are actually produced with a 24% blue percentage as the company is claiming. In other words, the sample data we got is not far enough away from 24%, from the 24% claim. That 16% is not far enough away for us to reject that. So what we're thinking about is when the sample data occurs with a low probability, we don't feel good about our initial guess, so we would reject it in favor of the alternative. When it occurs with a high probability, we feel pretty good about our initial guess. Okay, this number in the problem, the 14.3%, is called the p-value of the test. It's the probability value that you calculate. The p-value is the probability of your sample data occurring under the assumption that you initially guessed correctly. In other words, in this case, if the 24% claim is true, the null hypothesis. P-value is compared to the significance level in order to make a conclusion. If the p-value is less than alpha, that's your significance level, that means our sample data was far from what was expected, low probability of occurring, so we should reject our null hypothesis in favor of the alternative. Remember, the null hypothesis is your initial guess. If the p-value is greater than the significance level, then our sample data was close to what was expected, high probability of occurring, so we do not reject the null hypothesis. Okay, so in this case, this is what happened for us. We had p-values greater than the significance level. Our sample data was close to what was expected. 16% was not far enough away from the 24% claim, so we did not reject it. It had a high probability of occurring. So then the final question is, how would Tony's conclusion change if he only got 4 blue M&Ms in a sample of 44 M&Ms? Well, if he only got 4 of those M&Ms, p hat would be 4 out of 44, which was about 9%. Okay, So this is your 9% sample proportion. Well, we would take a look at that and we would look at the distribution. So where does it fall on our distribution? So if you really only got 9% blues, this should logically, it's like, whoa, I expect 24% blue, but I only got 9%. That should already, you should start like scratching your head like, wow, this is pretty far away from what I expected. So hopefully we would reject the 24% claim. So let's take a look at what we would do. So we go to our distribution over here. We find where 9% is, and we're going to look at 9% or worse. So if you look at this, right here, 9% is right about here, okay? And we see that value or worse, should really do like 9.1% because that's what it rounds to. There's 3 dots at that or worse. Look how far away 9% is from the 24%. It's really far away. It's super unlikely to occur. In fact, it only occurs 1% of the time that at this value or worse. This number, 1%, is less than your criteria you establish, your rejection criteria, the significance level. It is 1% is small, which means it's significantly different than what we expected to occur. That's why it's called the 5% is called the significance level. So our conclusion would be, since the p-value is 1% and is less than the 5% significance level, we reject the null hypothesis that the company actually produces 24% blue M&Ms. The evidence, which is our data, our sample data, suggests that the company actually produces less than 24% blue M&Ms. Do we actually know what that number is? No. We have no clue what the percentage would be. But this 9% that we got in our sample is too far away from what we expect, the 24%, for that 24% to even make any sense anymore. We don't know what the proportion is, but we feel pretty confident saying that it's probably not as claimed. Okay? So we're going to do more with this. If you have any questions, let me know.